Okay, welcome to week 4 of Applied Regression Analysis, and this week we're going to focus on polynomial regression. And this is really our chance to be able to use the analysis of variance table to examine models that contain more than a single independent variable. So now first I want to define what is meant by a polynomial of order k and x. And basically a polynomial of order k and x is an expression of this form: y is equal to c0 plus c1x plus c2x squared plus c3x cubed, and so on. This is a polynomial expression, and you can have any number of powers, up to the kth power. And the c's and the k are constants. Now, when k equal 1, we had y is equal to c0 plus c1x. That was a straight line. And now let's focus on the second order polynomial model, that is when k is equal to 2. So we have y is equal to c0 plus c1x plus c2x squared. Again, straight line model, we had a single x, power 1. Now we have two powers of x. One is power 1 and the other one is power 2. Now, by the way, these are mathematical models. The statistical model for the k equals 2 case can be expressed in one of two ways. First, we can write it as the mean value of y given x is beta naught plus beta 1x plus beta 2x squared. By saying the mean of y given x, we're talking about the fact that we understand that once we plug in x, we're not going to get y exactly. So we talk about this is the mean value, the mean response that we expect. Or we could write it this way, where we say y is equal to beta naught plus beta 1x plus beta 2x squared plus error. Okay, and the error, again, is this little fudge component that says, okay, the model may predict a little bit high or a little bit low. Told you that might happen, so we're going to put this epsilon term in just to make the model right. So let's use the method of least squares to obtain estimates for the regression coefficients for the second order polynomial model. And this estimated model, this estimated parabola, may be written this way: y is equal to beta naught plus beta 1x plus beta 2x squared. Again, the error sums of squares is just like before. It's the sum of the square deviations of each value of y about the predicted values of y. But now the predictions are based on the second order polynomial model. So it's y minus beta naught plus beta 1x plus beta 2x squared. So everything's the same. It's just that the prediction's different, but the sum of the square deviations is just computing the deviations about a different model. So, so here we have the least squares parabola. Notice that by putting in this square term, we allow the function to not necessarily be a straight line. It now has the ability to curve or to change. And we're going to choose the betas for this model, beta naught, beta 1, and beta 2, in such a way that the error sums of squares is smaller than it could possibly be for any other choice of betas that we could make. But instead of presenting here precise formulas for beta naught, beta 1, beta 2, which, by the way, can get very complex, especially if k is large, it's going to assume that you're going to be doing this work by computer. I mean, I always have students who will say to me, for me to really understand this, I really have to get my hands dirty. I really have to do the computations by hand. And I would say to them now that this is a good time to get over that, because you really need to have a good statistical package, fast computer, and you need to trust the computer package to be giving you the correct answers. So for the age and systolic blood pressure data with the outlier, now I've removed the outlier, not because that was a good thing to do or the appropriate statistical thing to do, but rather because we just want to try a different data set and see what the effect of supposing that we had a sample of size 29. And what I want to do now is I want you to jump ahead in your notes to the output, which you will find on page 109. And we're going to work our way through the output. We know enough to be able to do this, and then we'll come back and we'll fill in all the details when we come back to the notes. So notice that the first thing I did in the stata commands is I told it to drop the case if blood pressure was equal to 220. Notice that in stata language, this needs a double equal sign. So if the blood pressure is precisely equal to 220, drop the case. And so it finds that person whose blood pressure was 220, and if there were other people whose blood pressure was 220, they'd be dropped as well, but we know there's only one, and it drops it, and tells us that it deleted one observation. And now I'm ready to run the straight line regression, so I say regress systolic blood pressure on age, and I get this. Now we haven't seen this before because we haven't seen this analysis for 29 observations. So let's ask the same questions as we did before. Is this model, based on these 29 individuals, a better model than the naive model? Okay, and the naive model again would be one where you would simply predict that everybody has the average blood pressure. And the answer, of course, is yes, it is much better than the naive model, and you can see that because the value of f is 66.81, which is the mean square due regression over the mean square residual, compared to an f distribution with 1 and 27 degrees of freedom. And the p-value is very small, less than 0.0001. Notice that r squared, which again is the sums of squares due regression over the total sums of squares, r squared is 71.22%. So 71% of the variability in blood pressure can be explained by age alone for these 29 individuals that are left in the data set after I threw out the one person whose blood pressure was 220. See, it made a big difference to throw out the person whose blood pressure was 220, because I think in the other situation that we saw last week, when we didn't throw out the observation, r squared was only about 49%, if I remember. So here we have 71%. So we've explained a much higher percentage of the total variability with this one variable just by getting rid of that outlier. The other thing is that here are the coefficients for this model, and you can see that the model is 97.08 plus 0.95 times age. Okay, that's the model. Notice if I take beta 1 minus 0 divided by the standard error, you get a t of 8.17 compared to a t distribution with 27 degrees of freedom, right? You have a p-value less than 0.001. If you take this t value and you square it, you get an f of 66.81. So 8.174 squared is 66.81. The p-values are identical. A little confusing here because in the stat output they give 4 decimal places for the p-value for the f, but they only give 3 for the p-value for the t. But they're exactly the same test. Okay, they're telling us exactly the same thing, and that is in both cases, if you're interested in estimating blood pressure, you're much better off to know age than to not know age. Okay, it's good to know age. You get a better predictor. Now we generate a new variable, and the new variable is age squared, which is just age times age. You physically multiply age times itself, and you get age squared. And then you run the regression of systolic blood pressure. That's, again, the dependent variables listed first, systolic blood pressure, and then all of the independent variables in the model are listed next. So we get age and age squared are the 2 independent variables in this model. And so now we can ask the same kind of questions. If you're interested in estimating blood pressure, is this model a better model than the naive model? And again, looking at this and comparing, and again, the computation of f is the mean square for the model over the mean square for residual. And if you do that, 3136 divided by 88 gives you an f of 35.37 compared to an f distribution with 2 and 26 degrees of freedom. The p-value is less than 0.0001. Notice this is an f with 2 and something degrees of freedom. So there is no corresponding t. The only time you have a corresponding t is when you have an f with 1 and some number of degrees of freedom. So if you look at this, table now, a coefficient table, we have the model is beta naught 113.4 plus 0.0875 times age plus 0.0099 times age squared. That's the regression model. Each coefficient has a corresponding standard error. And t, we need to talk about this later, but for right now, we know about the significance of each of the coefficients. okay, and the overall f value. Okay, so this is a good place for us to stop, because after the break we're going to come back and we're going to take this information apart again as we proceed through the notes in more detail. So have a good break and see you soon.